Our goal is to model real-world systems. Homework problems out of a textbook are nice, but solving real-world applications gives us a chance to put our statics knowledge to work. So, what does it mean to model something? Well, it means to focus on the relevant details to answer a question. So, we're going to consider all of the physical phenomena that are occurring and then only focus on the relevant details to answer the question that we're actually after. So that brings us up to the first, all the steps. The first step of creating any model is to ask a specific question. And so what we're here looking for is a piece of information that can be answered with a number. How much does that box weigh? What's the maximum load that this table leg needs to support? Or what's the heaviest load that this crane can move? Once we've asked a specific question, we can move to the second step, which is deciding how accurate. For example, maybe we want to know how much a box weighs. Well, the accuracy that we need to know that answer for calculating shipping costs is quite different than if we're mixing sensitive chemicals. Maybe we need it in ounces for shipping costs. We might need it in micro ounces if we're mixing sensitive chemicals. Or if we're looking at what's the maximum load that a table leg needs to support. If we're just talking about a dining room table, plus or minus 10 pounds, probably good enough. Same story with the crane. Do we need to know how much this crane can move to the nearest pound? Or are we good even plus or minus, say, 100 pounds? In each case, that's going to help us decide the answer to question number 3 here, which is which phenomena matter? See, after we have a clear goal, we can ask ourselves what's actually relevant. So it's kind of interesting to think about, but gravity tends to usually matter, but maybe not. If we're dealing with something super lightweight, that might not be something we care about. What about friction? How about magnetism or buoyancy? Did you know that you actually have buoyancy forces acting on you in the air, not just when you jump in the water? And so if you were to go and stand on a bathroom scale, your weight is acting down, but the air that you displace causes a small buoyancy force up. Now, if you're just tracking your fitness, that might not matter. If we're deciding how much you weigh to put on a rocket ship, maybe we care about that little bit of an offset. Another example might be the friction inside of a pulley. So if we have some pulley and that pulley's got a rope passing over it, real pulleys have a resistance to rotation built in based on the fact that they are made out of two pieces of material that are sliding past each other. Well, we might care about that if it's a large resistance compared to the forces involved. So if we had, say, an ant and it's hanging from a piece of dental floss, we might care about the friction inside that pulley. On the other hand, if we were using that pulley with a big old cable to support a car, here's my awesome car drawing, then the friction force might be so small that it might not be worth the trouble. The point is, once we've done these 3 steps, now we get to move on and treat this basically just like the homework problems we've been dealing with. We're going to construct and solve our model using the same 4 steps that we've been talking about. We're going to build a free body diagram. We're going to come up with our force balances. Then we're going to use geometry to eliminate unknowns in those force balances. And finally, come up with an algebraic solution. So in general, we're going to encounter 2 types of systems in statics, particles and rigid bodies. And the big difference is that particles are point masses that don't have any extent, which means they can't displace or experience moments. But it turns out that particles aren't just some fictitious idealization. They turn out to be quite relevant in many real-world applications, depending on what we want to know. So, for example, maybe we are looking at a cup of water sitting on a table. If we need to deal with the forces of that cup of water acting on that table, then a point mass is all we really need to consider. And the table is going to push up on it with some normal force, and the weight of the cup is going to push down with some gravity force, which we could call, say, W. Even if we tilted that table slightly, well, that was pretty steep. If we tilted that table slightly, we still could think of this as a particle, right? What's stopping it from sliding down the table? Well, maybe now there is some friction force, F mu. We still have the normal force of the table. Those are the reaction forces. And then the applied load of the weight caused by gravity. Now, if we go too far, this won't work anymore, and we'll have to switch over and start treating it as a rigid body. If I tilt the glass this far, now what's happened is the center of mass of our cup of water has shifted way out to, say, here. And what we'll learn is that weight acts through the center of mass. We still have friction here, F mu, and the normal force here. And the question that we'd be asking is this thing going to tip over or is it going to slide down? And it depends on how steep we tip the table. And we could answer that question, but that would take a rigid body analysis. Rigid body. We cannot answer that with statics because now we're looking at forces with distances between them, and we'd have to sum moments to answer the question. So when can a real-world system be treated as a particle? Well, pretty simple. Any time we can ignore moments. Any time we can ignore moments. The trick here is just to draw the free body diagram and ask if the question that we're trying to answer can be found using the phenomena that we're trying to include. And also accepting that nothing in engineering is exact. There's always something we're leaving out because it has a negligible result, like your buoyancy on a bathroom scale. So let's go ahead and look at 3 common real-world considerations. These are going to be new things that we're going to learn about here. We're going to start looking at devices called pulleys. We're going to also look at devices called springs, and we're going to introduce one new physical phenomena called friction. And I don't want you to get too nervous here because basically what we're going to do is we're going to learn how to model the forces that act on each of these systems, and then you're just going to wrap that into your free body diagram and move on. So for example, a pulley may have a rope going over it, and that rope could have a weight here, and it can be fixed on the other end. And we're just going to learn how to draw a free body diagram for this system, which, by the way, is going to look something like this. We need a reaction force to hold the pulley up, and the force of the cable on both sides pulling down on it. When we look at springs and friction, I can actually draw you one picture that has both of those in it. So here is a spring, here's a mass, and it's sitting on a table, but we're going to include the effects of friction, which is indicated by that mu. We can do a particle analysis on this. The weight would be pushing down, the force of the spring to the left, the force of friction to the right, and the normal force of the table pushing up. And we're going to learn how to model these two forces. In other words, we're going to come up with some sort of an equation that describes what those forces are in quantifiable terms. No big deal. So, lastly, once we've done something like that, now we get to use the same solution strategy that we've always been using, which is to build a free body diagram, write out our force balances, do the geometry, and now sub in models for things like friction and spring forces, and then lastly, do the algebra to actually solve the problem. So you get to continue following the same 4 steps, and if you do, you'll never get stuck.